talk about some constructions that use as building blocks classical Riemannian geometry pieces, and mostly hyperbolic pieces in dimension 3, and construct invariants that have a quantum content. Most of it is, in fact, joint work with Tudor Dimofte at the Institute. He's sitting right there. It's an application of the use of classical geometry to get to some quantum field theory. So I'm going to start by saying that there are about 4 phases in knot theory. One phase is this algebraic topology that was practiced maybe until the 70s. And you hear words like the fundamental group, covering spaces, signatures, homology, intersection forms, linking forms, that type of math. Then around the 80s, early 80s, there was hyperbolic geometry, basically because of Thurston, who talked about Riemannian geometry invariants of knot theory. For instance, the fundamental group often carries a hyperbolic structure. So there are invariants such as the volume of a knot, the lengths of geodesics in the knot complement, incompressible surfaces, and so on and so forth. That was in the early 80s. Another phase was the Jones polynomial in 1985. It is a polynomial invariant associated with knots with integer coefficients, and it was quite different from the 2 before, soon to become topological quantum field theory with Witten and work of many others in the 90s. And finally, maybe a last phase was Chovanov homology in the year 2000, and the various forms of it, knot-Floer homology, that assigned abelian groups to knot complements that looked very similar to the algebraic topology of the 70s, except they were different in nature. So I want to talk about the connections between hyperbolic geometry and the Jones polynomial, and hyperbolic geometry and Chovanov homology. And I do want to start from hyperbolic geometry, such as sort of classical geometry, and then tell you afterwards perhaps a little bit about the Jones polynomial and about Chovanov homology. Okay, so what are hyperbolic structures in dimension 3? Well, so a hyperbolic structure in dimension 3, we mean a complete Riemannian metric on a 3 manifold with curvature -1. You probably know more about Riemannian metrics than I do. Such a metric satisfies a nonlinear PDE, namely the Einstein Equation. Okay. So such a metric can be exactly computed for the following reasons. So why can we compute it? I will not give the PDE reasons that may allow you to compute this metric, but I'll give you some alternative reasons. So to tell you these reasons, first of all, let's recall what is hyperbolic space, or at least one of the models of hyperbolic space. With metric, the usual hyperbolic metric. At an element. So that's hyperbolic space. It has an isometry group, orientation preserving isometries, which is a rather specially group. It's PSL2C, so SL2C modulo plus or minus identity. And therefore, a hyperbolic metric G gives, so G gives a representation of the fundamental group of the manifold into PSL2C. And not only gives, but G can be reconstructed from this representation. This representation is 1-to-1. And in addition, the image is a lattice. This is the so-called discrete faithful representation. All right. So the next thing is that there is most of rigidity, which implies that this is unique up to conjugation. Yes, did I not? Yeah, sorry, I mean, everything is finite volume. Yes, thank you. This M should be finite volume. Okay, but a corollary of most of rigidity in particular is that the representation can be defined over a number field. So in particular, if you look at traces of elements of the fundamental group, and since it's P, maybe we take the square to be well defined. It doesn't really matter. And we look at the collection of these complex numbers. Well, that is a number field. This is called the invariant trace field. And in fact, the representation itself is defined over a quadratic extension of the invariant trace field. Said differently, these fundamental groups are finitely generated, in fact, finitely presented, and typically, in fact, they are generated by two generators. I mean, not always, but typically. Therefore, to know the representation, it suffices to know two matrices with entries in some number field. That is an exact computation, an exact statement. And knowing this, you know the complete hyperbolic structure. That's why it can be exactly computed. Okay. So Thurston, in the late 70s, introduced something called the gluing equations, which is a system of polynomial equations to compute this discrete faithful representation rho 0. And by compute, I mean to compute exactly, numerically, and effectively. And one of his students, Jeff Weeks, in the early 80s, implemented that and made the first census of about 10,000 hyperbolic manifolds. So the gluing equations themselves is a system of polynomial equations, in fact, a zero-dimensional system of polynomial equations whose solutions are algebraic numbers, which are related and can reconstruct the representation in question. There is a catch. The catch is that we need an ideal triangulation of the manifold with cusps, of the hyperbolic manifold with cusps, and by that I mean whose non-empty boundary is a union of tori. So in order to write the equations, we need this. From the point of view of invariance, it is unfortunate that you have to choose an ideal triangulation. However, the fact that there are ideal triangulations and that these triangulations are related by a set of moves has sort of postmodern consequences that relate very well to Chovanov homology, for instance. So maybe it's not a bad idea that we have to choose an ideal triangulation, and it's a reflection of something much more modern. Okay, so I will tell you now about what the gluing equations are, how to understand them a little bit, the shape of these equations, and their invariants. So the building blocks for the gluing equations is an ideal tetrahedron. So what is an ideal tetrahedron? Well, you can compactify hyperbolic space whose boundary is the complex numbers union the point at infinity. And conformally, at least, it's a sphere. And if you have 4 points in the sphere, you can take the convex hull of 4 points in a sphere, and that is an ideal tetrahedron. The convex hull of 4 points in the boundary of hyperbolic space. And ideal tetrahedra have shapes. Why? Because the isometries act triply transitively on the points of the boundary. So we can bring 3 out of the 4 points, 3 points to 0, 1, infinity. And we're left with the 4th point. And the 4th point is Z, a number in C minus 0, 1. Although this is joint work with Tudor de Mofte, I must say that a lot of this work was actually motivated by conversations with Don Zagier. It's sort of not an accident that this appeared in a previous talk too. Okay, so this extra point, Z, is the shape of the ideal tetrahedron. So ideal tetrahedra have shapes Z. So we can say TZ is the ideal tetrahedron of shape Z. And what do these shapes really mean, other than the definition as a convex hull? Well, if an ideal tetrahedron delta is oriented and if we choose, so let me draw it the way we draw Euclidean tetrahedra. So if we have an oriented ideal tetrahedron, and if we choose a pair of opposite edges, let's say for consistency this one, then there is a unique way to assign complex numbers z, z prime, and z double prime to the edges as follows. So opposite edges get the same value, where z prime is 1 over 1 minus z, and z double prime is 1 over 1 minus z prime, which is also 1 over 1 minus z. And note that z, z prime, z double prime is minus 1, and z double prime and z inverse minus 1 is 0. Okay. So if we have an ideal tetrahedron of shape Z, then we can really assign shapes to all the edges according to this rule. Then there is a little geometric lemma that says that the argument of a dihedral, well, that the dihedral angle is the argument of the shape of the edge. So for instance, the dihedral angle here is going to be the argument of Z, of the ideal tetrahedron. So if we use the ideal tetrahedra as building blocks, we can put them together along a triangulation. So let T be an ideal triangulation of an hyperbolic manifold M oriented with cusps and let's suppose that Zi is the shape of delta I after a choice of quad. That means a choice of opposite edges for every ideal tetrahedron. So if we have this data, the ideal tetrahedra themselves have hyperbolic structures, and if we put the structures together along an edge, we will the consistency condition that the metrics match is a condition on the shapes. For instance, if you put the ideal tetrahedra along a common edge and you go around the tetrahedra of the edge, the sum of the dihedral angles should add to 2 pi. That's a condition, that is a linear condition on the arguments of the complex numbers Z. So the gluing equations have the shape sum of logarithm Zi with some integers plus Bij So this is the shape of the gluing equations where these numbers are integers. And the number of equations is the number of edges of the ideal triangulation. And an Euler characteristic argument tells you that if you have n tetrahedra, then you have n edges. So these are the n gluing equations. There are a couple of additional ones, usually called Cusp Equations. They have the same shape, except that they add up to, well, not to pi I, but to 0. And they have to do with the holonomy of the peripheral structure of the meridian and longitude. Okay, now you may actually think that this is not an algebraic system of equations since I'm taking logarithms of complex numbers, and we know logarithms are multivalued functions, so the immediate kind of question is what exactly do you mean by the logarithm of a complex number, an arbitrary complex number, right? So to get rid of this difficulty, so we can get rid of the logarithms and also get rid of one of these equations, which is redundant. Any one is redundant, and keep one cusp equation. Okay, and exponentiate. And then we get something like the product of zi to the a bar ij, zi prime to the b bar ij, zi double prime to the c bar ij is plus or minus 1. In addition, we can use the product of a z with a primed and doubly primed version is minus 1. And we can use the choice of the quad to eliminate one of the z or primed or doubly primed. So we can eliminate using the choice of quad one of z, z prime, z double prime in each tetrahedron to get to a system of equations that look like this: aij, zi double prime, bij is plus or minus 1. And we can write it more schematically, getting rid of all the indices. We write it as z to the a, z double prime to the b is plus or minus 1, where a and b are n by n matrices with integer entries. Okay, so this is the system of gluing equations. Maybe and it's a theorem of Thurston, is that this system is zero-dimensional, that if tau is a regular ideal triangulation, then these gluing equations is zero-dimensional. And one of the solutions of the gluing equations recovers the complete hyperbolic structure. And one solution recovers the complete hyperbolic structure. Let's do an example. There is the knot 5-2. I have not drawn that. There is only two knots with 5 crossings, a torus knot and the other one. This knot 5-2, for this knot, the matrices A and B, you can choose them to be this one. And the vector here of signs, you can choose it to be -1, 1, 1. In other words, there are three parameters, z1, z2, z3, and the system of equations looks like z1 inverse, z2 inverse, z3 inverse. Z1 double prime is -1, z1 inverse, z2 double prime is 1, and z1 inverse, z3 double prime is 1. Keep in mind that z double prime is 1 over 1 minus z. So this system of equations simplifies to z2 equals z3, and z, which determines z2 and z3, satisfies a cubic equation, z cubed minus 2z squared and 3z minus 1 is equal to 0. It has three solutions. One of them is this one. And this solution recovers the complete hyperbolic structure. In particular, the invariant trace field in this case is a cubic field. Okay, so once we have a hyperbolic structure described this way, what can we compute? So one of the best known invariants for a manifold, hyperbolic manifold, is the volume. It is not totally obvious that non-compact manifolds, such as knot complements, have finite volume. Well, it isn't obvious that an ideal tetrahedron has finite volume, but it does. And in this case, I'll do the example of the volume of 5,2. That is the volume of TZ1 and volume of TZ2 and volume of TZ3, which is the sum of a special function, a single special function, which is nothing but the Bloch-Wigner function, argument of 1 minus z times log z. Bloch-Wigner dilogarithm. It is a period, or the imagined part of a period. Okay, so in other words, what we learn from this point of view is that if you choose a regular ideal triangulation, then you can express the volume as a rational linear combination of algebraic numbers to which you have applied a regulator function, the Bloch-Wigner dilogarithm. As far as I know, this statement doesn't follow from a PDE point of view, and it would be very interesting to know why these algebricity results follow from the existence theory. Okay, so that's the volume. What else can you do? Well, that was kind of all that you could do. Maybe you can calculate something called the Chern-Simons invariant using this method, whose volume was the imaginary part, in fact. But it was a little hard to get to invariants of hyperbolic manifolds using ideal triangulations. Let me mention another invariant which is not defined using ideal triangulations. other invariant is the torsion the Reidemeister torsion of the discrete faithful representation. Unfortunately, it is a little difficult to define this invariant for several reasons. First, the representation is not acyclic. Second, the representation does not take value in a compact Lie group. And third, there are deformation issues associated with that. But it is possible to define them. The invariant defined, in fact, by Porti originally. And moreover, this definition allows you to show that it isn't just a complex number, but an element of the invariant trace field as well. The definition of the Reidemeister torsion starts by using a presentation of the fundamental group, and it is essentially a determinant of the Fox matrix of derivatives after you apply the representation to make into a matrix of complex numbers. Okay. So now I want to give you an alternative definition of what turned out to be an invariant of three manifolds using ideal triangulations. So we are going to fix some oriented hyperbolic manifold with cusps. And we're going to fix a regular ideal triangulation tau. And we're going to fix a choice of quads. And fix an edge that we drop one of the edge equations. And with this, we can consider the following quantity, determinant of A times diagonal Z double prime and B times diagonal inverse of Z times Z to the F double prime Z inverse to the F, where delta of Z means diagonal and Z to the F double prime means Z1 to the F double prime 1. It is a monomial. And as about these Fs, and the Fs are flattenings the Fs are flattenings. They are integer solutions to a system of inhomogeneous linear equations. I don't want to talk too much about them because they don't play a very fundamental role. So one thing that is obvious is that this quantity is an element of the invariant trace field, and I'm only going to consider it up to a sign. Okay, so and our theorem is that tau is independent of the above choices. Okay. And also independent of 2-3 moves of regular ideal triangulations. Let me remind you what a 2-3 move is. It is a combinatorial move. So these are combinatorially 2 tetrahedra on one side, and they are exchanged to 3 by putting this extra edge. Okay. So now let me tell you some facts about 2-3 moves. A regular means that if you write the gluing equations, they have a solution which recovers the complete hyperbolic structure. Yes. Non-degenerate, yes. So the fact is that any two ideal triangulations are related by a sequence of 2-3 moves. This is Matveev and Pergolini. So we can say X to be the set of ideal triangulations made into a graph by putting an edge when you perform a 2-3 move. So this set is connected. This graph is connected. Then there is the subgraph of regular ideal triangulations. And this is not known to be connected. That is a problem that really has nothing to do with hyperbolic manifolds. It is a problem that has to do with regular triangulations of 3-dimensional polytopes. You can choose them to be Euclidean. It's a combinatorial statement. And it's known that in dimensions more than 5, the corresponding statement is false. In dimension 4 is open, and in dimension 2 is trivial, because every polygon can be triangulated to triangles, and every 2 triangulations of a polygon are related by a sequence of 2-2 moves. Here is a 2-2 move. Okay. The edge goes from here to here.
You mean just like the top to the bottom?
Yep. Okay. Now, although this is not connected and it ought to be connected, it has a canonical connected component, the Epstein-Penner connected component. So every complete hyperbolic manifold as above can be can be decomposed into ideal polyhedra, which themselves can be triangulated. And for triangulations of those polyhedra, the corresponding 2-3 moves can be performed. Therefore, this is a connected component. So if you want to get a number out of this invariant, which is associated to the 3-manifold M, you can choose an ideal triangulation, which is a refinement of the canonical one, compute the invariant, and that is your answer. So we can get an invariant at the end of the day, which associates an element of the invariant trace field to the manifold itself. Okay, so the proof of the theorem is combinatorial as long as we understand what happens to the gluing equations when you make a 2-3 move, for instance. So a new edge appears. This new edge belongs to exactly 3 ideal tetrahedra. So there is a new equation that these ideal tetrahedra satisfy. It's a local equation. You have to analyze the portion of the matrices that involve that edge. It's a fully combinatorial, you may say boring, worthless argument, except that it is the same type of argument that you do when you study algebraic K-theory using symbols. So exactly because it is combinatorial and over Z, it actually may have a little more meaning. Okay, so we get an invariant. So then we also have a conjecture, and the conjecture is that tau is equal to the Reidemeister, up to a sign. That is a conjecture. So both invariants take values in the invariant trace field of the manifold. Therefore, this is a conjecture about exact quantities. And you can numerically confirm well, we used about 2,000 digits. For all knots with 14 crossings. Okay, the right-hand side can be computed using Nathan Dunfield's program, and the left-hand side, we wrote the program ourselves. So it seems to be correct, but a proof of this conjecture is not within reach. How do you relate the fundamental group to this sort of datum is not clear. And, well, now I want to give you a whole power series invariant, not just one number, one numerical invariant, but a whole power series invariant for a hyperbolic manifold. So I need some preliminaries. So we're going to use some special function. What is our special function? F, variables here. It's exponential of sum of h times a polylogarithm, but a negative polylogarithm. Okay, so this is a power series in X and H1 half. To be independent of the triangulation, we have not proven it. They also ought to coincide with the asymptotic expansion of the Kashaev invariant of a knot. That is why we say that they have a quantum content. So every term of the series is an element of the invariant trace field, but the whole series itself is supposed to capture the color Jones polynomial at a root of unity. Well, I guess I didn't really talk at all about the relation to Hovanov homology, but this is another knot, a torus knot, in fact. And if you did the SL3 color Jones invariant of this torus knot, you'd find out that it stabilizes in a certain way to some power series in Q. These power series in Q are products of unary theta series in this example. You can prove this identity, but in general are not known to be Mach modular forms at all. So I'll stop here.